On December 7, 1941, the battleship West Virginia lay berthed at position Fox 6 in Pearl Harbor. She was a Colorado-class vessel displacing over 32,000 tons. She was a massive floating fortress designed to trade punches with enemy capital ships at ranges of 20,000 yards or more. But on this morning, the physics of her survival would be determined at point-blank range. She was moored outboard of the USS Tennessee, which placed her hull directly exposed to the open channel. When the Japanese air attack commenced, this position transformed the battleship into an unintended shield for the vessels trapped inboard. The geometry of the harbor meant that the West Virginia absorbed the full kinetic fury of the first wave. The primary instrument of her destruction was the Type 91 aerial torpedo. In the span of minutes, the ship was struck not once or twice, but 7 times on her port side. 7 torpedoes represents an overwhelming amount of high explosive energy concentrated against a single structural plane. Each detonation acted like a hydraulic hammer against the hull plating. The water pressure amplified the blast, forcing steel inward and opening massive rents in the anti-torpedo protection system. The ship also absorbed 2 bomb hits from dive bombers. One was a 16-inch armor-piercing shell converted into an aerial bomb, which failed to detonate but possessed enough kinetic mass to punch through the superstructure decks. The other struck the port casement level and ignited a fire that would burn for 30 hours. But the bombs were secondary. The immediate threat to the life of the ship was the hydrodynamics of the torpedo damage. When a battleship takes massive damage on one side, the physics of buoyancy change instantly. The port side voids filled with thousands of tons of Pacific Ocean water. This asymmetrical weight distribution created a violent listing moment. The ship began to roll to port. In the berth ahead, the USS Oklahoma was suffering a similar fate. The Oklahoma had no chance to correct her balance, and within minutes she rolled completely, overtrapping hundreds of men inside her hull. The West Virginia was seconds away from replicating this disaster. The inclinometer on the bridge was tilting dangerously past 20 degrees. The righting arm of the ship was collapsing. In this chaos, survival required a decision of cold mathematical logic. Lieutenant Claude Ricketts was the assistant fire control officer. He understood that you cannot stop the ocean from entering a hole 40 feet long, but you can negotiate with gravity. Ricketts ordered the damage control teams to initiate immediate counterflooding. This is a terrifying command to give on a sinking ship. It requires the crew to intentionally flood undamaged compartments on the starboard side. It seems paradoxical to let more water into a vessel that is already dying, but the physics are undeniable. By flooding the starboard voids, Ricketts introduced a counterweight that fought against the port side list. The water poured into the starboard tanks and the massive hull groaned under the strain of 2 opposing hydraulic forces. Slowly the leverage shifted, the roll to port arrested. Gravity pulled the ship down evenly. Instead of capsizing and trapping her crew in an inverted steel tomb, the West Virginia settled upright into the harbor mud. Her keel struck the bottom at a depth of 40 feet. The counterflooding had worked. The superstructure remained above the surface, and the main deck was awash but level. The cost of this survival was high. The ship was a burning wreck. Her captain, Mervyn Bennion, had been mortally wounded by shrapnel on the bridge, yet continued to command until the end. The fires raged until the next day, fueled by leaking oil and ammunition. But because the ship remained upright, the recovery of survivors was possible, and the salvage engineers were left with a manageable geometry. If she had rolled over, she would have been a total constructive loss. Instead, she was merely resting. The Japanese pilots believed they had removed her from the board permanently. They had only changed her state of readiness. The West Virginia was now a submerged steel problem sitting in the mud waiting for the engineers to calculate her resurrection. 7 torpedoes should have rotated the hull 180 degrees. In almost every simulation of naval combat available to the United States Navy in 1941, that much explosive energy concentrated on one flank results in a capsize. The fact that the West Virginia stood upright was a statistical anomaly, but while the counterflooding had saved her orientation, it could not save her structure from the laws of physics. The battleship was now sitting on the bottom of the harbor, and the damage she had sustained was catastrophic. The 7 torpedo impacts had not created 7 distinct holes. The blasts were so close together that they had merged into one massive continuous wound. The port side of the hull was effectively erased for a length of over 100 feet. The steel plating had been shredded like aluminum foil. The internal bulkheads, which were designed to compartmentalize the ship, were blown inward or disintegrated entirely. The ocean did not just enter the ship, it occupied it. This damage profile exposed the limitations of the defense philosophy used to build her. The West Virginia was constructed on a principle known as all-or-nothing armor. This design strategy concentrates the thickest steel protection around the vitals of the ship. The magazines, the engine rooms, and the command centers are encased in a heavy armored box often called the citadel. The logic is that you cannot armor the entire ship without making it too heavy to float. So you armor the critical areas heavily and leave the bow, the stern, and the underwater hull relatively light. The intent is to defend against high-velocity artillery shells coming from the horizon. However, the Type 91 torpedoes did not care about the armored citadel. They struck below the heavy armor belt or at the precise junction where the belt met the lower hull. They attacked the unarmored buoyancy chambers that kept the heavy citadel afloat. The explosion energy traveled the path of least resistance, which was through the thin lower hull plating and into the voids. The all-or-nothing scheme worked exactly as designed against gunfire, but against a saturation torpedo attack, it simply ensured that the heavy armored box would drag the rest of the ship to the bottom. The violence of her sinking introduced a second structural complication that the salvage engineers had to address. When the ship settled, she did not land gently. She slammed into the harbor floor with a displacement weight that had effectively doubled due to the intake of water. The floor of Pearl Harbor is not a flat concrete slab. It is an uneven mix of mud, coral, and debris. The impact was so severe that the bottom hull plating of the battleship deformed. The keel and the lower strakes were forced to conform to the topography of the seabed. This created a permanent distortion in the ship's spine, a phenomenon the engineers described as wrinkling. Naval divers were sent into the dark water to map this chaos. These men worked in zero visibility, guided only by their hands. They crawled through the jagged steel teeth of the torpedo holes. They had to distinguish between twisted wreckage and structural supports. Their reports painted a grim picture. The West Virginia was resting in 40 feet of mud and oil. She was stable, but she was not watertight. To bring her back to the surface, the salvage team would have to seal a hole that was barely distinguishable from the rest of the ocean. They could not use standard patches. The curvature of the hull was gone, replaced by a jagged void. They would have to build a new hull out of wood and concrete while the ship was still submerged. You do not fix a battleship with steel alone. When the scale of damage exceeds the capacity of standard naval repair techniques, the engineer must look to civil construction for a solution. The West Virginia had an open wound along her port side that was too large for welded patches. The steel edges were too distorted and the gap was too wide to simply plate over. To make the hull water tight again, the salvage team had to construct a new temporary hull out of wood and concrete. The primary structure used for this repair was the cofferdam. In naval salvage, a cofferdam is essentially a watertight fence built around a damaged area to allow water to be pumped out. For the West Virginia, the engineers prefabricated massive wooden patch sections. These were not small planks. They were heavy timber structures reinforced with steel bracing designed to withstand the immense hydrostatic pressure of the ocean at 40 feet. Naval divers maneuvered these sections into place underwater. They had to align them blindly in the darkness of the harbor, ensuring that the wood covered the jagged rents in the steel armor. However, a wooden patch cannot seal perfectly against a hull that has been wrinkled by impact with the seabed. The bottom edge of the cofferdam sat against the twisted metal and the harbor mud, leaving gaps where water could rush in as fast as the pumps could remove it. To close these gaps, the Navy turned to a technique used in building bridge piers. They used Tremie concrete. Pouring concrete underwater is a paradox. If you simply dump wet concrete into the ocean, the water will wash away the cement binder before it sets, leaving you with a pile of useless gravel. The Tremie method solves this through fluid dynamics. The concrete is fed down a watertight pipe. The key to the process is that the bottom end of the pipe must remain buried deep inside the pile of fresh concrete being poured. This ensures that the new concrete flows out from the inside of the pile, never coming into direct contact with the water until it pushes to the outer edge. The surface crust may degrade, but the internal core remains pure and hardens into a solid rock seal. The salvage crews poured tons of this mixture along the bottom edge of the wooden cofferdams. They effectively cast a new concrete foundation for the ship while she was still sitting in the mud. This concrete plug filled the irregularities of the wrinkled hull and sealed the gaps that the divers could not reach. It was a crude solution, but it was chemically sound. Once the concrete cured, the wooden patch was sealed against the steel hull. On May 17, 1942, the pumps were engaged. The physics of the situation reversed. For months, the weight of the water inside the ship had pinned her to the bottom. Now, as the pumps transferred that water back into the harbor, the buoyancy of the hull returned. The ship groaned as the suction of the mud broke. Inch by inch, the West Virginia rose from the bed of the harbor. She was no longer a sunken wreck. She was a floating vessel, again held together by timber concrete and the stubborn application of engineering principles. But as the water level dropped inside the hull, it revealed the human cost of the delay. The salvage team had solved the mechanical problem, but they were about to confront the biological reality of what had happened inside the dark compartments during the sinking. Time is usually measured in hours during a salvage operation. Engineers calculate tidal cycles and pump rates in minutes to ensure the stability of the hull. But deep inside the submerged compartments of the West Virginia, time was measured in marks on a calendar. As the salvage teams lowered the water level inside the ship, they were not just recovering a military asset. They were breaking the seal on a tomb. The process of de-watering revealed the human cost of the attack that the ocean had hidden for nearly 6 months. The recovery operation was gruesome work. The interior of the ship was coated in a thick layer of heavy fuel oil and harbor muck. In total, the salvage crews recovered between 66 and 70 bodies from the dark interior of the vessel. Most of these men had been trapped by the immediate inrush of water or the fires that raged on the main deck. But the most chilling discovery was found in compartment A111. This was a dry provision store room located deep within the ship. When the salvage team forced the watertight door open, they found the bodies of 3 young sailors. They were not burned. They were not crushed. They had evidently found shelter in the compartment as the ship settled on the bottom. The evidence found with them told a story of methodical survival. The men had access to a supply of fresh water and dry rations. They had flashlights and batteries to fight the darkness. They had lived in the cold silence while the battle raged above them, and while the salvage divers worked on the hull just feet away. We know this because of a wall calendar found next to the bodies. One of the men had used a red pencil to mark off the dates. The crosses on the calendar did not stop on December 7th. They continued for over 2 weeks. The final mark was placed on December 23rd. These 3 men had survived for 16 days on the bottom of Pearl Harbor. They had likely died only when their oxygen supply was finally exhausted in the airtight space. The realization that men were alive inside the ship while she lay on the mud was a psychological blow to the salvage crews. It highlighted the terrifying isolation of a sunken ship. Even with the fleet base just a few hundred yards away, the physics of the airtight compartment created an unbridgeable distance. This discovery also underscored the mechanical principle of buoyancy that controlled the operation. Buoyancy is the force that opposes the weight of an immersed object. It is a transaction between displacement and density. For the West Virginia to rise, the engineers had to remove the weight of the water inside her. By pumping out the flooded compartments, they reduced the density of the ship until it was less than the density of the surrounding harbor water. This generated positive lift, but this lift came with a consequence. The water had acted as a barrier that preserved the interior conditions. As the pumps ejected the water, they transferred the load from the harbor floor back to the ship's structure and simultaneously exposed the wreckage to the air. With the water gone and the dead removed, the West Virginia was no longer a tomb. She was a hull ready for reconstruction. The ship was patched sufficiently to float on her own. She was refloated and moved to a dry dock where the temporary concrete and wood patches could be replaced with steel. But the Navy decided that a simple repair was not enough. The ship was too valuable, and the war was far from over. She would not just be fixed, she would be transformed. The West Virginia was ordered to steam to the Puget Sound Navy Yard for a complete modernization that would alter her fundamental geometry. 114 feet is a problematic number for a United States Navy battleship in 1944. It is problematic because the lock chambers of the Panama Canal are only 110 feet wide. When the engineers at the Puget Sound Navy Yard finished the reconstruction of the West Virginia, she was physically too wide to pass through the canal. This was not an oversight, it was a calculated strategic decision. By widening the hull beyond the canal limit, the Navy was effectively locking the ship into the Pacific Ocean. She was no longer a two-ocean asset. She was a dedicated weapon forged solely for the destruction of the Imperial Japanese Navy. The reconstruction of the West Virginia was total. When she arrived in Washington state, the shipyard workers stripped her down to the main deck. The cage masts, which had been the signature of the American battle line for decades, were cut away. The superstructure was removed entirely. In their place rose a compact modern tower that resembled the silhouette of the new South Dakota-class battleships. But the most critical work was done below the waterline. The vulnerability exposed by the torpedoes at Pearl Harbor was the lack of depth in her underwater defense. To fix this, the engineers welded massive anti-torpedo bulges to the sides of her hull. These steel blisters added layers of void space and liquid loading to absorb explosive energy before it could reach the vitals. This expansion pushed her beam to that critical width of 114 feet. While the hull was made tougher, the mind of the ship was made sharper. The West Virginia received the most advanced sensor suite available to the fleet. The centerpiece of this upgrade was the Mark 8 fire control radar. In the previous war, and indeed during the attack on Pearl Harbor, naval gunnery was an optical science. It relied on men looking through glass lenses to estimate range and bearing. It was limited by daylight weather and smoke. The Mark 8 removed these constraints. Fire control radar works by transmitting a pulsed radio beam that reflects off a target and returns to the ship. By measuring the time delay of the echo, the system calculates the range with a precision that the human eye cannot match. It feeds this data directly into an analog computer that adjusts the gun elevation for the motion of the ship and the rotation of the Earth. This technology meant that the West Virginia did not need to see her enemy to kill them. She could fight in total darkness. She could fire through smoke screens. She could track a target 20 miles away at night and land 16-inch shells on its deck with mathematical certainty. This technological leap transformed the ship from a victim of surprise into a predator of the dark. She was now a paradox. She was an old battleship with a top speed of only 21 knots, which was slow compared to the new fast carriers. But she possessed a level of situational awareness that was decades ahead of her construction date. She was heavy stable and bristling with new 5-inch dual-purpose guns and automatic anti-aircraft cannons. In September 1944, the work was finished. The West Virginia completed her sea trials and turned her bow west. She did not go back to patrol the safe waters of the coast. She steamed directly for the Philippines. The outcome path for this vessel was now locked. She was not returning to the scrapyard, and she was not relegated to convoy escort. She was heading for the Surigao Strait. The Japanese Navy was assembling a force to contest the American landings at Leyte Gulf, and the West Virginia was sailing to meet them. The ship that had been sunk by surprise at dawn was about to engage the enemy in the middle of the night. At 0300 hours on October the 25th, 1944, the ocean was black. The Surigao Strait is a narrow passage of water in the Philippines, and on this night it became the setting for the last battleship duel in history. The USS West Virginia was steaming slowly at the center of the American battle line. She was accompanied by 5 other battleships, including her sister ship, the Maryland and the Tennessee. 5 of these 6 ships were veterans of Pearl Harbor. They had been raised from the mud, patched, and modernized. Now they waited in the darkness for the Japanese southern force to sail into their trap. The tactical geometry of this engagement is known in naval warfare as crossing the T. This is the ideal position that every admiral since the Age of Sail has dreamed of achieving. The American fleet was arranged in a horizontal line across the top of the strait. The Japanese column, led by the battleship Yamashiro, was steaming vertically up the strait. This meant that the Japanese ships could only fire their forward guns at the enemy, while the American ships could bring their entire broadside batteries to bear. It maximized the volume of fire for the defenders while minimizing the return fire of the attackers. It was a firing squad arranged on a nautical scale. While the other older battleships struggled to find a target in the radar clutter of the narrow strait, the West Virginia had a clear picture. Her Mark 8 fire control radar pierced through the darkness. At a range of 22,400 yards, the radar operators locked onto the leading Japanese battleship. This range was extreme. It was over 12 miles. In daylight, hitting a moving target at that distance is difficult. At night, it should have been impossible. But the fire control computer generated a firing solution that was stable. At 0352, The main battery commander gave the order to fire. The 8 16-inch guns of the West Virginia erupted. The recoil force of the salvo was so violent that it shook the entire ship, but the modernized hull absorbed the shock. The shells arced through the black sky for nearly a minute. On the radar screens, the operators watched the pulses of the shells moving toward the target echo. When the shells arrived, they did not just land near the target, they bracketed it. The radar operators observed a specific phenomenon on their scopes that confirmed the accuracy. They saw the hard, consistent return of the steel ship, and momentarily they saw the soft, transient returns of massive water geysers erupting around it. These were the shell splashes. The difference between the hard return of the hull and the soft return of the water confirmed that the West Virginia had straddled the Yamashiro with her first salvo. The subsequent salvos tore the superstructure of the Japanese battleship apart. The ship that had been sunk by surprise was now delivering the death blow to the Imperial Japanese Navy from a distance where she could not even be seen. The destruction of the Yamashiro marked the end of the effective Japanese surface fleet. The West Virginia continued her service supporting the invasions of Iwo Jima and Okinawa. She survived a kamikaze hit and continued to fire her guns until the final days of the war. When the surrender documents were signed in Tokyo Bay on September 2, 1945, the West Virginia was there. She was anchored in the same waters as the enemy capital. Her journey from the bottom of Pearl Harbor to the victory in Tokyo Bay is the definitive case study of naval salvage. It proves that a warship is not defined by her initial loss. She is defined by the engineering capacity to recover her. The West Virginia was destroyed by physics in 1941. She was resurrected by engineering in 1942. And she was vindicated by ballistics in 1944. She remains one of the rare battleships to be sunk at her birth, raised by salvage, rebuilt for war, and then brought back to fire in the last battleship duel in history.